Hello, good morning, everybody. I hope you are all doing well. You're enjoying your stay at home. I know it's sometimes boring, but use your time wisely. Do some things, try to learn new things. You have the internet, you have everything next to you. And do not forget to read your math notes. Okay, keep yourself updated to math lessons. So this is a continuation of previous lesson. Today we are going to have activities. We will apply some notions that we have learned so far on few examples. We are still with the same chapter 15 and it's section 2. Let's start from the first activity. Let's take this example. Find the angle measures of the inscribed quadrilateral. My quadrilateral is LKGM or GKLM. So first we need to find what? To find the value of x. So what is the theorem saying? It says an inscribed quadrilateral in a circle has its opposite angles supplementary, right? So MK are supplementary. The angle LG also are supplementary. So we start by taking one of these pairs. Let's take the pair L and G. We set our equation. We say that the measure of G plus the measure of the angle L equals 180. Okay, then we substitute with our expressions here. So for G, it is 39 plus 7x degrees plus the measure of L, which is 6x minus 15 equals 180. Now we simplify. This is 13x plus 24, that is equal to 180. We subtract 24 from both sides and we divide by 13, and our x is 12. Now we are not done yet. We found x, but the question is asking about the measures of these angles. So what we are going to do now is to substitute the value of x in each of these angles. So we started by the measure of G. It's 39 plus 7 times x. Our x is 12, so mg is 123. The same thing for ml. We substitute x at 6x minus 15, which is 57 degrees. For the measure of k, it is 20x over 3 degrees. My x is 12, so the measure of the angle k is 20 times 12 divided by 3, which is 80 degrees. Now, what about the angle m? We know that m and k are supplementary, so the measure of m plus the measure of the angle k is 180 degrees. The measure of k is already found, which is 80. I solve this equation, so I subtract 80 from both sides, then the measure of m is 100 degrees. So G is 123, L is 57, K is 80, and M is 100. All right, let's take two other examples. Find the measure of each angle of inscribed quadrilateral TUVW. We do the same. So using the theorem, we set that the measure of U plus the measure of W equals 180. So 12Z minus 27 plus 37 plus 5Z is 180. I simplify my equation. Then this is given 17Z plus 10 equals 180, and Z is 10. All right, I'm sure you know how to solve this kind of equation. You're more familiar with these. Now, what is the measure of T? I found Z to be 10, so I just go to the expression and substitute for Z. It is 125 minus Z, which is 10, so it is 115. U also it's 12 times Z, meaning 12 times 10 minus 27, which is 93 degrees. Finally, we have V is 180 degrees minus 115, which is 65 degrees. Why? Because V plus T is 180. They are supplementary. Now W is 37 plus 5 times Z, which is 10, so it is 87 degrees. Now look at this question. What must be true about a parallelogram that is inscribed in a circle? I have a parallelogram inscribed in a circle. What is going to be true for this parallelogram? We know that the parallelogram is already a quadrilateral. So we know that the parallelogram opposite angles are congruent, right? Opposite angles of the parallelogram are congruent. But also, for this parallelogram to be inscribed in a circle, its opposite angles should be summing 280. So, in which case, the opposite angles are congruent and they are supplementary. It's only in one case, when they are 90 degrees. At that moment, my parallelogram in fact is what? Is a rectangle. Remember, we said that the rectangle is a parallelogram. It's a type of parallelogram. So, if a parallelogram is inscribed inside a circle, then this parallelogram must be a rectangle. And all of its angles are 90 degrees. Remember the definition of the rectangle. Alright? Question. Can my parallelogram that is inscribed inside this circle be a square? What do you think about this? Yes, it can be a square. Why? Because a square is a type of rectangle. So in some cases, yes, my parallelogram can be a square. Alright? Let's move to this example. I have L, M, and P is a quadrilateral inscribed in a circle. Alright? If the measure of L equal to the measure of N, L and M are congruent. That's what's mentioned here. Okay. The question now says, is MP a diameter for a circle or not? Explain. What does the diameter mean? It means the segment MP passes through the center of my circle. Now the question, is this true or not? Now let's use this. We have ML equals to MN. The measure of L equals to the measure of N. They are congruent. And at the same time, I have that they are supplementary. Why? Because it's an inscribed quadrilateral inside the circle. So M of L plus the measurement of N equals 180 degrees. Again, if you have these two conditions, two angles are congruent and at the same time they are supplementary, so these angles should be measuring to 90 degrees. This plus this tells you that the measure of L equals to the measure of N and equals to 90 degrees. Now, if my angle is 90 degrees, what does this remind you about? It reminds you about the inscribed angle of a diameter theorem. Remember we said that if we have an inscribed angle that is 90 degrees, okay, then its ends are part of the diameter MP. Alright? So L is 90, N is 90, MP should be a diameter for this circle. So this is true. Now, question. If it happens that the length LP equals to the length PN, how can you use this information to prove that the shape MLPN or this quadrilateral is a kite? How? Very easy, by looking at these triangles here, MLP and MPN. If I prove that they are congruent, then my shape is a kite. Why? Because remember, from the definition of the kite, we said that two pairs of congruent sides. So if LP equals to PN and LM equals to MN, then this should be a kite. Now, look at this, guys. Look at this triangle. I have a common side, which is PM. I have the angle L and N are congruent. And if I said that LP is equal to PN, then now, guys, I have a question here. Suppose that you are given this information that LP equals to PN. What can you say about this shape here? Which type of quadrilateral is this? What do you think, guys? Does it look like a kite? Do you remember what the kite is? Yes, in fact, this is a kite. How can I prove that this is a kite? Look, the definition of the kite says that two consecutive sides like this, LP and PN, will be congruent, and another pair from the other side, which is LM and MN, are congruent. How can I prove that LM and MN are congruent? I will look at these two triangles here. So I have a common side, which is MP, common between the two. All right, and I have these two angles are equal, and I'm given that LP equals to PN. Then the triangle LPM is congruent with the triangle MNP. They are congruent means MN is congruent with ML. Now the definition of the kite says this, and this shape will be a kite only if you are given that either LP equals to PN or ML equals to MN. I'm saying this because, look, if I change the position of L, I make it, for example, around here where LP is not equal to MN. Look at this position. Yes, look at this position, guys. What do you think about it? L is still a right angle, no problem. But is this shape now a kite? No, because this length here is not equal to this. So that's only a kite when you are given one of these lengths here is equal to the other one. All right, guys. Well, this remark is out of the problem. I've just added it for you to see if you still remember something about kites and quadrilaterals. So you should be updated. Thank you for today's session. Please join my classroom at classroom.google.com using the code MEOXYX3 and send your questions, your remarks, your answers if you tried one of these questions, and see you in the next session. All right, take care of yourselves, sleep tight, use sanitizers. See you soon.